Okay. Can people hear me? Too loud? Too quiet? Okay. Hi. So I'm Narek. I'm a graduate student here and also working on these kind of things. And today I'll talk about learning switches and the spanning tree protocol. So the goal is to walk through some examples with learning switches and the spanning tree protocol, and kind of stress what we have learned through the online lectures in Murphy's recordings, and look into the corner cases of where the protocol, where are some interesting things that don't happen all the time, but we should think about and test our understanding that we understand the whole flow right. And yeah, there will be a lot of these red boxes on the slides, which are questions, and then the goal is to get those answered in class, and then there will be a green one afterwards with the answer, but please do answer them because all of this is review, none of this is new material. This is from Murphy's lectures, but we do cover some corner cases that isn't directly in the lecture, so it would be good to go over them and test our understanding. And Alex also had this, so if you have answered questions before and you want the reward, raise your hand. And yeah, Alex, should I give it to you to pass? And yeah, I'll try to propagate them with some algorithm with my questions as well. Yeah. Feel free to use DV to pass these around, by the way, if you remember how that works. So learning switches. This is the diagram that we're going to use. The S's, S1, S2, S3 are the switches, and A, B, and C are the hosts. Something like this should be familiar from lecture as well, where we were talking about learning switches. And the goal is to go through this and see how learning switches actually learn. Like these S1, S2s are our learning switches, and they are going to learn about our endpoints. And here in the process, we are going to go step by step and see how the switches learn about the endpoints. Again, just remember the distinction between these and the other routing algorithms we had used. Like both Alex and Murphy had mentioned that these are kind of not seeded. So there is no pre-configured information. There is no control plane traffic. All of these switches are going to learn about our end hosts, but by just merely looking at actual data packets and data communication. If this diagram right now isn't clear, speak now, because in next 30 minutes or so, we're going to constantly see this. So make sure this makes sense. So we now have these destination next hop tables that the switches are going to maintain, and in this learning process, they are going to fill this in. Do we need a table here? No? Why not? Yeah, because these are end hosts, right? They don't maintain any routing state. They just have some traffic they need to send and receive, and they are just doing that. Okay, so we now start with the learning switches. There's some message going out. A is sending out this message. Who is this message meant for? Can it be like S5? No. Anyone? Because yeah, messages are meant for end hosts. We don't send messages to the switches. And then as this is being propagated, this is just a data packet. This is not control traffic. It's meant for some, like we said, it's meant for B. And S1 receives this and is going to pass forward. But before passing forward, is there anything that S1 can learn from this traffic? Yeah, so it can fill in the entry that it can get to A through its direct next hop. It's directly connected to A. And then since S1 doesn't know where to forward it next, it doesn't have an entry for destination B, it just is going to do this flooding. So by just sending this out on all the outgoing ports except the one that all the ports except the one it came from. And as this packet propagates, the other switches on the route will also learn the route back to A. So this is just a regular data packet, nothing special in it. But as it goes forward, it leaves this trail by which the switches learn how to reach A. And then typically when you send something to an end host, usually the communication is two-sided. B is going to send something back. And if this happens, then on the way back, it is going to leave a trail of how to reach to B. And then the switches on the way back will learn that as well. Yeah? S1. Yeah, it did, right? Uh, does anyone know? Yeah, right? It's just going to look up its table, and it has a route already. And so it won't need to. Am I doing bad with the candy stuff? Or okay, next one. So now let's say we have a new host D that's being connected to S1. And then A is sending a packet to D. Would this be flooded? You seem determined. Anyone? Do we have no's? I don't know if I should throw and I don't know the rules here, but yeah. So it might be confusing, and it shouldn't be because it doesn't know even if it's directly connected. It hasn't been really pre-configured to know about this route. In distance vector, we said that these are directly configured, and we go and we say these two are connected to each other. But in learning switches, this is not the case. Nothing is pre-configured, and even if it seems that it's directly connected, it still doesn't know about it. So yeah, the answer is it would be flooded. So if we say the end host D never sends, when will the switch actually learn about B? What is it? Which one? Who responds back? Oh, the assumption is D never sends anything. So yeah, when D never sends anything, it'll never, the switch will never learn about it. Questions? Okay, so we remember from lecture that this is all good until we actually have loops. And then here, if we introduce the additional link there, we now have a loop, and this causes a problem. And the problem is that if now end up flooding, if A sends something and S1 ends up flooding, or if D sends something and S1 ends up flooding, then this flooded packet is going to go around and around in our network. Is the problem worse when we have more than one loop? Yeah, it is bad in that we have some packet that's going to go around, and then at some point its TTL will reach and it will disappear. What happens if we have more than one loop? Yeah, it will duplicate because every time it ends up near this loop point, both of them are going to propagate, and so we're going to spend more and more bandwidth on these things. So it's really bad because it can just consume all of our bandwidth. But so far, we also previously had underlying topologies that had loops, right? Both when we were considering link state and when we were considering distance vector, the underlying physical topology often had loops. And we said it's a good thing because it adds redundancy. So how did we deal with loops there? This is a candy-worthy answer. Split horizon. Yeah, in link state, we had sequence numbers when we were sending this around. And in distance vector, we weren't really flooding. So the same kind of thing doesn't happen. If we have one packet, there is no point where we're actually duplicating it, sending out twice. Even if we had loops there, even without split horizon, when we had loops in distance vector, we never duplicated packets because we were just sending the same packet around. And for link state, we had sequence numbers. And we don't have sequence numbers here because, well, we can't. These are just data packets and hosts communicating with their other end hosts, so we don't really have a control protocol. All of these are just data packets. So we just saw that we can't use the underlying topology for doing flooding with these learning switches. And spanning tree protocol is what's going to help us to solve this. And spanning tree protocol helps us create a spanning tree on top of this loopy topology, which ends up being loop-free. So we construct some tree, and then we will only use this tree and assume the other links for now just don't exist. We'll use this tree to do our flooding. So let's consider some end results of trees that we can actually, like some trees, and see whether they would be valid trees or not. Like, let's say, and then yeah, the legend there shows what different types of links are. In the beginning, we just start we don't know where any link is in our spanning tree or not, and then as the protocol runs, we either add them to our spanning tree or disable them and never send anything over them, never flood over them. And this is one example of a tree. Would this be a valid tree for forwarding, for flooding? This would be a better picture with the other loops. Just nothing there. This is valid, right? Yeah. Would the spanning tree produce this, the spanning tree protocol that was described in lectures? Because? So it keeps closer, further ones? So which link would be different, for example? Uh-huh. Okay, we're actually going to run the algorithm. So I don't remember on top of my head which one would be different, but it seems we at least agree spanning tree protocol would not produce this. And we have some understanding of why. Yeah, one example, I think that's what you were saying, is S5 would connect to S2, would use that link instead of connecting to S3, right? And this is because we had this thing of breaking, using smaller IDs of switches. That's right. This is another one. Would this be produced by the spanning tree protocol? Yeah? Do we all agree? Yeah. Mm-hmm. Yeah. So this would also not be the one that we end up producing. This is the underlying topology we were using before we introduced the loop in the underlying topology. But the topology actually changed the spanning tree that we would end up using in a spanning tree protocol. Which may seem unintuitive, but if you follow the protocol to the letter, then you'll figure out that this is what's happening. This is another one. No, did we do this one? Yeah. Did I give away the answer by asking that? Yeah, would this ever be produced?